Okay, it's Rob here from HiPy. Welcome back to the third in a series of videos for physicists. Last video we started to plot our data and we got this lovely graph here. What we really want to do is determine the location of each of these peaks in both of these spectra. So we've got the copper K alpha and the K beta lines here. Okay, how on earth are we going to do that? Well, we're going to do it the good old-fashioned way. We're going to fit a Gaussian to each of these peaks, right? So I've got a bit of a blurb here as to why exactly we have to do that. Make sure you understand in your mind why you want to get those peak locations out. I'm just going to cough, hang on. Right. I'm going to fit each of those with a Gaussian curve shape. So if you don't know what a Gaussian is, now's the time to Google it. I'm going to use this this formula here, where alpha is, A is the amplitude of your Gaussian, x0 is the midpoint of the Gaussian, and sigma is the standard deviation of that distribution. Okay. Excuse me. Right, so let's first create a function for that. Now, if you're not familiar with creating a function in Python, go and have a look at the introduction materials provided by HiPy at the links above. But to create a function, you always start with this def command here, okay? So it's going to be def, and then I'm just going to call it Gaussian. Okay, now I'm going to open the brackets, and what comes next is very, very important. I'm going to tell this function what to look for in terms of variables when it's run. So I'm going to put all of my x data in. So x, and I'm going to call a series of parameters which I'd like to submit to that function in an array. So I'm going to put an asterisk here. Now I'll come and talk about that in a second, and I'm going to call it params for parameters, right? Okay. Now when you're defining a function, any function, you write your first line in your function, you define its name and the parameters, and you put a colon after it. Boom! Right? And you can see when I hit enter, it will automatically increment the next line. So you can increment with a tab or 4 spaces. I always use 4 spaces, but it's up to you. Now, I'm just going to write a bit of, I'm going to write a comment here. So to write an extended comment, I'm going to use the 3 quotations. I'm going to go up, and I'm going to write some stuff, right? So I'm going to write x must be an array. Okay, and I'm going to write params must be an array of a, x0, and sigma values. Okay, so I'm essentially sending the variables that describe the shape of my Gaussian and the location of it as a list into that function, right? And I'm going to return an array the same length as x. Okay, so they're essentially my y values that I'm returning for that Gaussian. Okay, so my line shape. Now that hasn't done anything yet. All that is useful for is for me in future to understand what that function is doing. I definitely recommend that you comment your functions. Well, I'm going to have to edit out some of these coughs. Okay, first thing I'm going to do is I'm going to get a value for a. Now that's coming from my variable params, but I'm saying that's the first variable in that list. x0 is going to be the second, and the sigma, or the standard deviation, is going to be the second, okay? And I'm going to return this epic function above here. So let's actually write that in Python. How do we do that? So we've got a, and that's divided by, right, open brackets. Now I need to put a square root in there. I'm going to use numpy to do that. npy dot square root, call square root, and everything in the brackets is going to be that then. I'm going to call npy again for a value of pi. I'm going to close that, and I'm going to multiply all of that by this exponent. So again, to get an exponent, I'm going to use numpy np.exp. I'm going to open up my brackets. I'm going to open up brackets again to get the top half of the numerator of that fraction. And I'm going to put x minus x0. I'm going to close that. And to do squares, I'm going to do double asterisks. Okay, not a sort of hat sign like you'd use in Excel. I am going to, actually I want to put, yeah, that's right. And that's all over. And I'm going to open this up and I've got 2 times sigma. And again, all of that is squared. Okay, and now I'm just going to control and enter that. So let's test out this function, right? Let's make sure it works. So to test it out, I'm going to give it, I'm going to define a completely arbitrary x list. Let's call it x is equal to, I'm going to use the amazing line space. I use this all the time, line space. And I'm going to say it's going to go from 500 to 500, the same as our data above, and I want 200 points in that list, okay? And then, to get my y values for my Gaussian, I'm going to go y, I'm going to call that function I called Gaussian above, and I'm going to give it the x list, and I'm going to give it my, let me just think what I'm doing. Yeah, I'm going to give it all of those values for a, x0, and sigma, right? So let's just for some random values in here. Let's call it 1,000. Oh, comma. You need a comma. 1,000. Let's put. I don't know why I'm gonna put another 1,000 in there. And 100. Okay, so it's an amplitude of 1,000. Ah, that was silly, wasn't it? Spotted that. An x0 position of 1,000 and a standard deviation of 100. Okay. And then I want to plot that. Now I'm not going to bother to create the matplotlib figure that I did in the last video. I'm just going to go plt.plot x, y, and don't forget plt.show. Okay, see what happens. And there you go. I've got a Gaussian shape, right? And I haven't labeled my axis, but that's okay because I just wanted to check that that function was working. How do we go about using that now to fit our data? Right. So let's guess some parameters for our Gaussian to fit the data. I don't think the ones we've used above are that bad, but let's look at the data. Let's look at our plot again. Let's try which plot are we going to fit here. 1,700. So this is our gain equals 2. And I reckon there's about, our copper K alpha here, let's fit this peak, right? Our copper K alpha here is at about 1,700, okay? So let's try and fit this. So let's give it a guess. Let's see what the amplitude is. So anywhere between 0 and 1,000 for the amplitude is going to be fine. And we'll guess the standard deviation. Let's create a guess. Let's call it guess 1. So I'm going to let's just use an amplitude of 500, and 1,700 is going to be the x0 position, and let's just say it's got a standard deviation of 50. These are probably, so other than the location, the other values are probably completely wrong, but it's okay because we're going to fit that data. Now I'm going to use HiPy, which is another Python library, to fit this. And if you want to read more about the curve fit of that package, optimize.curvefit, go and have a look here, read the documentation, it'll tell you everything you need to know. But for now I'm just going to import that module. Don't forget to import the modules you need, so that's going to be import scipy.optimize. Best way to do this actually is from scipy import optimize. That's that way I can just call it using the word optimize, okay? And if you go and read the documentation on that function, you'll see that this optimize method returns 2 variables as lists, and I'm going to call them popt. I'm going to put it up here actually. Popt, So they are the optimized parameters for my Gaussian, which is fitted to the data. And it also returns another one which I'm not too worried about, and that's the covariance of those optimized parameters. Okay, so let's call my optimize function, and I'm going to use optimize curve fit is the method I'm using. Now I'm going to use the function above that I've defined, which is my Gaussian. Okay, I'm going to feed it my x1 and my y1 data. Now remember what that was. That was the real data that I read in from my Excel spreadsheets for my copper data at a gain equals 2. Okay, and I'm also going to give it a value of p0, which is the variable name that it's expecting to see. And I'm going to give it my guess. Okay. Now, let's control and enter that to make sure I'm not getting an error. Okay, so I've got a warning. Now, that's okay. Sometimes you get these warnings when using the other packages. If you don't want to see a warning like that, or they get a bit annoying, I include this line. I include this line above here. Let's just run that, and the warning goes away. Right? Now, I'm pretty sure it's actually fitted that curve, fitted that peak. But let's have a look. Let's have a look what p-ops looks like. Okay, so this was the x0 value that was interesting, and that's told me that's 1722. Now that looks about right. Amplitude of about 758 and a standard deviation of about 30. That looks about right, but let's just check that that fits by actually plotting a figure with our data and our fit on it. Okay, so again, remember how to create your figure axis? Fig ax equals plt subplots. Okay, and let's plot the data. Can you remember how to do that? That is, I'm going to do it slightly different this way because I want to distinguish between my data and my fit. Right. So for my data, I actually want a nice scatter plot. I want each of the data points to be a distinct dot rather than a line. See, they're joins them all together. So I'm actually going to use a scatter plot for this, ax.scatter. And again, I'm going to put in my x and y values, so x1, y1. And I'm going to put s equals 1. Now, that defines the size of the dot on the figure. I'm sorry guys, I got a stinking cold. Right. And I'm also going to label my data. Call it data. And we can define the color as well. Let's do that. Otherwise, I think the default is blue, but let's define it, right? So I've got my plot. And let's just check that that's going to work. Plot.show. Yeah, looks good to me. So that's my copper 1, my copper with a gain equals 2. I got those two peaks. Remember, I'm fitting this peak first. And let's truncate that axis a bit by doing ax.set xlim 1500 to 2250. There you go. Looks a bit better, doesn't it? See a bit more what's going on. And let's add our fitted Gaussian to that plot. So ax.plot x1. So I'm using the same x values that I've got in my data. x1. I'm going to call my Gaussian function again. And I can put the x values in. And now I'm going to use my p optimum values, which I fitted above. Close that. So they're all my y values. And then I'm going to label as a fit. There you go. Let's show that. Ta-da! What have I forgotten? Boom. There you go. So that looks pretty good. I've got a really good fit for my K alpha peak here at about 1720 plus or minus a standard deviation of 42. Does XEU look about right? Yes. Okay. So what happens if I want to fit? What happens if I want to try and fit this peak now? Okay, let's try and do that very, very quickly before I stop breathing. I'm just going to insert a new sound here. Let's go down a bit. Alright, so let's try and fit the K beta peak. So my guess 2 for this one, well, this looks like it's got a much lower amplitude, so let's call that 100. And it looks like it's about, let's say 1950. Well, let's use the same standard. Let's use the same standard deviation that I guessed in the first place. And again, I'm going to get my p-opt. Let's call it p-opt. Yeah, I can do that. Let's use the same variable. It's a bit naughty if I can use the same variable name, right? Pcurve equals optimize curve fit. Call that Gaussian again. x1, y1, x and y data, and this time I'm going to use a p0 is equal to guess 2. Does it work? Yes. What does that p-opt value look like? Ugh. So call that again. Okay, so it's given a value of 1. It's given the exact same values as my original fit. So it's trying to fit this curve, but because it's sort of, this peak is so much more dominant, it said, nah, you're all right, mate. I'm going to do this curve instead. So this is a problem now. So I'm really going to have to think hard about how to fit both of these curves simultaneously. And of course there's a way to do that, and I can take what I've got already, which is this Gaussian curve shape. I can say, okay, this time I'm going to fit 2 Gaussians. Okay, so I'll define another Gaussian in the next video, another function, sorry, which has 2 Gaussians in it. And I'll try and fit both of these simultaneously by giving it guesses for both peaks respectively. So we're going to do that in the next video, if I survive. Okay, right. Thanks for watching. I'll see you later.